Okay, thank you. So I'm very glad here to present our work evaluating a research garbage collector in Google's production environment. And in this talk, we will talk about how did we improve over the state of the art by 9%. And in PRDI 2022, we published the ELXA garbage collector paper. And in the paper, we discussed that ELXA generally has better performance than other OpenJDK collectors. But in the paper, we still left some threats to validity. We set out to productize ELXA, but before that, we need to address these limitations. The question here is that whether can we do that without sacrificing the performance? In detail, we evaluated ELXA in Google's productization environment. Productizing a garbage collector is not easy. Most of the OpenJDK garbage collectors took over 5 or even 10 years to become production ready and also being adopted in industry. So for example, G1 was published in 2004 and it became production ready in 2009. This is also the same for the other 2 modern JDK collectors, Shenandoah and ZGC. ELXA GC took a very different approach and also innovative approach comparing to the OpenJDK collectors. Due to the time, I'm not going to discuss all the technical details. Please refer to the ELXA paper for more details. I'll just quickly go through 2 high-level design components. First, ELXA uses reference counting to improve reclamation immediacy. We add 3 temporal coordinate optimizations. We first adapt deferral RC so that we can postpone the processing of stack pointers to the upcoming GC pause. And then we adapt the coalescing RC optimization. This observes that, as shown in the middle of the screen, if a pointer is updated multiple times, all the intermediate pluses and minuses, they can all be canceled out. We only need to apply the first decrement and the last increment. And we also adapt implicitly dead optimization. This allows us to ignore young objects. With all these 3 optimizations, we use reference counting to achieve timely reclamation while still having great performance. ELXA also uses image space to perform opportunistic evacuation to reduce evacuation overhead. The image space divides the memory into 32K blocks, and blocks are further divided into 256 bytes lines. A block can be a mix of occupy lines and free lines. For the free lines, as shown in the green span in the screen, image space is able to directly reuse these lines for allocation without any copying. And for the fragmented blocks, for example, the block on the left, we still want to evacuate them. Similar to the other implementations, we do a small transit closure to copy the remaining live objects out of the block. But during this process, we can still reuse the existing lines for allocation without having a large copy reserve. And this is how we use image heap to perform judicious and targeted copying. We only need to do a small amount of copying, and we can do that totally in the pause without the expensive concurrent copying. And the workload we chose to evaluate ELXA is called LSJ. It stands for latency sensitive Java. The whole LSJ environment has a lot of challenges. For example, it uses G1 as its default GC, but G1 on LSJ is highly specialized and optimized. It has no concurrent marking and only performs young GC. But young GC cannot reclaim mature memory, so G1 still needs to periodically trigger the expensive full GC. But this will also directly lead to large pause time and high tail latency. To mitigate this, LSJ introduced a mechanism called lame duck. Whenever G1 wants to do a full GC, LSJ will directly shut down the server and redirect all the requests to some other servers until the full GC is finished. Basically, all these setups makes G1 performing extremely well on LSJ. And also, LSJ requires a fully featured GC. To make ELXA working with LSJ, we need to add multiple missing JVM features like compressed pointers, class unloading, and weak references. Also, LSJ is complicated and restricted. It's a huge workload running on a shared machine, and it contains user-sensitive data. All these restrictions making directly debugging on the LSJ server extremely difficult. So to simplify our process, we came up with a systematic methodology called pathology mapping to help our debugging. So it is an iterative process. The idea is really simple. In each iteration, we first find a pathology on the production server, and then we map the problem to a locally manageable benchmark. After we figure out the problem and fix the problem, we map the solution back to the production server and evaluate. By repeating this process multiple times, we solved many correctness and performance issues. I'll just pick one example to demonstrate how this works, the virtual space fragmentation problem. Basically, LSJ uses a JVM feature called compressed pointers, and it only supports up to 32 gigabytes of contiguous virtual memory. And LSJ also sets the heap size to 31.5 gig, right on the boundary of the max memory limit. This means that the heap now is very sensitive to the memory fragmentation. G1 solves this problem by performing expensive full heap compaction in full GCs, but the consequence is that it can also lead to high pause time and high latency. LXR has no compaction, so we started to see out-of-memory crashes. We applied pathology mapping to solve the problem. First, we observed the symptom that LXR crashes a lot due to out-of-memory. Because it was extremely difficult for us to directly debug on the server, we had to map the problem to a locally manageable benchmark. We used a couple H2 to reproduce the problem by setting heap size to 31.5 gig. Although H2 was the largest workload in the switch, it's still relatively small. The live set size is only around 700 meg. Setting heap size to 31 gig did not actually change anything. So we had to create a variant of H2 that uses much larger live set size, which is around 20 gig. And with this larger H2, we were finally able to reproduce a problem, and the problem was about inter-chunk fragmentation. In general, LXR has two spaces, the immix and the large object space. They manage memory chunks at different granularities. When the two types of chunks are mixed with each other, it creates huge fragmentation in the heap. And LXR has no compaction to quickly reduce that fragmentation, so we eventually start to see out-of-memory errors. After figuring out the problem, we tried a few solutions or workarounds. First, we still don't want to do compaction because we want to avoid large pause times. And one workaround we did is to set a clear boundary between the two spaces so that the chunks won't mix with each other. Also, we tried to reduce the heap size for LXR so that it can be more tolerant to the fragmentation. After verifying those solutions on the couple H2, we ported them back and evaluated on LSJ, and it totally worked. So basically, we applied this process multiple times to solve many performance and correctness issues on the server. And now let's look at how LXR's performance eventually looks like. So in terms of our evaluation, LXR is implemented in MDK with OpenJDK 11. And here we use two different couple benchmarks for evaluation. We use the 2022 dev snapshot to reproduce the original LXR results. And we also use the stable release to evaluate the latest fully featured LXR. We compare two LXR versions, the original one and the latest one that is fully featured with all the correctness and the performance optimizations. And we also compare three different OpenJDK collectors, G1 and Shenandoah from JDK 11, and G1 from JDK 21. 21 was the latest LTS at the time of our evaluation. This table is a reproduction of the original LXR evaluation, and it measures the total execution time, and we normalize the results to G1's total execution time. We report the numbers on three different heap factors relative to G1's minimum heap. The green column is the original LXR. So first, it's less stable, so we could only report 17 out of 22 couple benchmark results. And also, it does not have support to some of the important JVM features. We had to disable class unloading, weak references, and compressed pointers to all the GCs here. And this column is the latest LXR. We can see that the latest LXR significantly improved the performance over the original one. Especially on the small two heap factors, we can see a 9% of total time reduction. And also, the latest LXR is now consistently better than all the other OpenJDK collectors. This figure evaluates the latest fully featured LXR, and we also report the total execution time normalized to G1. And the latest LXR, first, it's much more stable than before. It can run on all the 22 benchmarks. And it's fully featured with support to all the missing JVM features. In the figure, the blue bars are G1, the green bars are LXR, and the yellow bars are Shenandoah. We can see that on most of the benchmarks, LXR generally has better performance than other two collectors. And if you look at geometric mean, we are now 11% better than G1. And we also compare G1 in JDK 21. The latest G1 in JDK 21 improved the performance over the G1 in JDK 11 by around 6%. But our LXR, which is implemented in JDK 11, still outperforms the G1 in JDK 21. And this is the same as this graph. This graph shows the 99.99 tail latency normalized to G1. And we can see that LXR also generally has lower latency than other collectors, including G1 in JDK 21. And how did LXR eventually perform on LSJ? First, we made LXR and MDK stable enough to run on the LSJ server for sufficiently long. So this is important for us to show that both LXR and MDK is strong enough to run production-grade workloads. Also, we eventually made LXR having similar performance to that specialized G1 in terms of tail request latency. But to do that, we still need some special tricks. For example, for now, we had to disable lazy RC decrements. Otherwise, it may harm the mutator performance. Hopefully, in the future, we will completely resolve this issue. Another problem blocking our project is that Google has moved to JDK 21 and we are still on JDK 11. We are not yet done. In the future, we will and hopefully after we port it to JDK 21, we will restart this project and making Elixir even better. And basically, many research artifacts were brought into industry every year. We are not the only one. But few of them ever share their lessons and insights. We are very glad here that we can publicly share our lessons we learned from our project. They are all actionable lessons, and we believe they will be helpful for the future productization efforts. Due to the time, I'll just quickly go through 3 out of the 5 lessons. The first one is that a systematic combination of research and production methodologies can meet production objectives while simultaneously advancing the research state of the art. We deployed the Elixir in a production server, and as a result, we also improved the Elixir's performance by 9%. And productization experiences can and should strengthen research workloads. We upstreamed one example. Our example is that we contributed to decouple benchmarks to make it have stronger benchmarks which uses larger life set size and better mirrors the real workload behavior. And L5, replacing core technology in industry is a challenging socio-technical problem. In terms of adopting new technology, many companies are often blocked by many non-technical issues. For example, long-term maintenance costs, restricted environments, and commercial concerns. These are not covered in our work, but we still need to be aware of this. And finally, I also like to add some discussion to the productization dividend. Basically, at the start of the talk, I mentioned that adding missing features to the research artifacts will likely to degrade the performance. But as we've just discussed, that we finally reaped a productization dividend of around 9%. We feel this both surprising and disconcerting. This suggests that work that incrementally advances an established production system will tend to profit from a built-in productization dividend, while entirely new work will not. Until we are aware of this, we will prefer incremental work over new ideas. Elixir was built from ground up. We were very lucky that Elixir was slightly better than G1 at the very beginning. But imagine what if Elixir in 2022 was 1% worse than G1 instead of better. We would less likely to publish the Elixir work, and we will probably never see the outcome today that we eventually made Elixir 11% better than G1. But this does not imply weakness in the algorithm. It's just at that time, we did not have this productization dividend. Okay, so conclusion. We evaluated Elixir in production, and we yielded Elixir that is fully featured, more stable, and with 9% performance improvement. We developed a systematic pathology mapping process to help our debugging, and we also discussed our 5 actionable lessons and productization dividends. We hope all of this will be helpful for the future productization efforts. And we are not yet done. In the future, we will continue fixing existing issues and evaluate Elixir on more workloads. And we are also going to port Elixir to more runtimes, including V8 and Android runtime. And hopefully by doing so, in the future, we can see a state-of-the-art garbage collector to work on multiple language runtimes, not only Java and OpenJDK. Yeah, thank you. Any questions?
All right, please come up to the microphone with your questions.
Hi, my name is Krishna Nandiwada from IIT Madras. Very interesting piece illustrating your experiences.
Yeah.
I had a question regarding the evaluation. In the paper, you say you run it for 5 runs and take the performance, but our experience with Dacapo benchmark has been the first K runs. I mean, Steve knows it very well. First K runs, K goes to 15, 20 also. Many times the variation is too large. And I'm just curious here.
It's just I did a preliminary evaluation on Dacapo benchmarks. Our conclusion when we were doing the evaluation is that for 5 iterations of the runs, we can get relatively stable results. So this is why we mainly choose to run for 5
With 5
iterations.
runs, you could get stable runs?
Yeah, that's from our results. We can get relatively stable results after the 5 iterations.
Okay. Thanks.
Hi, very interesting work. When translating work to productization, I'm coming to difficulty to keep up the pace of the updates. For example, you mentioned Android runtime here. Android runtime updates once a year, and everything is changing. The interpreter, the JIT, and then garbage collections are all changing. So I come into the difficulty to keep up the pace of the updates. So I wonder, do you face the same difficulty, and do you have some suggestions for this?
We haven't faced this problem on LXR, but we do have this problem on MTK. So our lessons for now is that we will try to upstream the part that's related to those runtimes as soon as possible, so that they can be maintained as part of the runtime. And their upstream maintainers will spend, say, extra effort, for example, spend some cost in the CI to evaluate the integrity of our system. So that will be much easier instead of like maintaining our open source project and keep tracking the upstream changes.
Okay, thank you.
Yeah.
Thanks, Wenyu.
Hey.
So you mentioned the lame duck strategy, right,
Yeah,
for G1. Do you still need to resource to that as well for LXR? Do you experience some, I don't know, you need to redirect it to a different server to do defrag?
Currently, when I was doing the evaluation on the server, I disabled this mechanism for LXR. So it can totally work, but actually we did not observe any change. Well, the server has a lot of extra complications. For example, the servers, it is extremely difficult for us to directly measure the performance on the server because the server is actually, for example, the QPS, it depends on the time of the day. And because it accepts and processes real user requests, so it actually depends on which time you are running the server. And the results are really difficult to reproduce. So we could not have a, say, sound way to reason like how many performance change we observed after disabling this feature.
Right.
But we did disable that on the server.
Gotcha. Thank you.
Let's sing this Peter one more time.
Yeah, thank you.